Okay guys, I welcome you all to Engineers Academy. Do subscribe my channel if you haven't done it yet. Now we are going to solve these two problems, which says that determine the magnitude of the moment of the force F, which is given as a Cartesian vector, about the baseline AB of the tripod. And similarly, we are given the same force and we are asked to determine the magnitude of the moment of the force about the baseline BC. So we have to find the moment about this AB line and this BC line. So to solve the first problem, let's say that the moment of the given force about AB magnitude, this will be equal to the unit vector along AB and the dot product with the moment of the force F about point A or point B, right? So let's say that we define our position vector, that is the moment arm. Let's say that the moment arm is R, and let's say that the moment arm for this force F is, let's say, from B to D. Let's say that this is my moment arm from B to D. Let's say so this is RBD. We can select AD as a moment arm, right? Since the moment arm or the position vector can be any vector from any point on the axis of rotation. Let's say if you want to find the moment about this AB line, so this position vector from can be any position vector from any point on this AB line to the line of action of that force F. So this force F is the line of action of this force F is passing through that point D. So we can select any position vector from that axis of rotation. So our axis of rotation for this particular problem is AB, since we want to find the moment about that line AB. So we can choose the position vector or the moment arm from B to D, or we can choose the position arm from A to D. So I will choose the position vector from B to D, since in the second problem we are going to find the moment about the BC line. So this is our BC line, and for BC line we can choose this C to D as a position vector or this B to D as a position vector. So if we determine this position vector from B to D for the first problem, for this problem, then we will be able to use that same position vector from B to D for the second problem as well. So we can conclude that the moment arm of a given force can be any vector from any point on the axis of rotation to the line of action of that force F. So we can choose infinite many position vectors, the moment arms from this A to B. We can say that this can be our moment arm, we can say this can be our moment arm, this could be our moment arm. So we can select as many moment arms as we can, and the moment arm need to start from the axis of rotation to the line of action of the force F. Now for this particular problem we are going to use the B to D. So this B to D position vector is my moment arm for this given force F. So now to find this, to use this equation, we have to find the unit vector from A to B. Now the unit vector from A to B is equal to the position vector from A to B divided by its magnitude. So now the position vector from A to B is, so from A we need to move to write the position vector from A to B, we need to travel from A in the direction of X, Y, and Z to reach that point B. So from A we need to travel this much distance from along the x-axis. So this much distance along the x-axis is 2 plus 1.5, so this is 3.5. so this is, we can write this is plus 3.5 in the positive I, and then once we reach here, then we need to travel this distance in the positive y direction, 0.5 meters in the positive y direction. So I will write plus 0.5 j, and since point B is on the floor, it is in the xy plane, so there is no need to travel along the z-axis, so this will be 0k. Now the magnitude will be this 3.5 square plus 0.5 square plus 0 square under the square root. So this will give us the magnitude, which is square root 3.5 square plus 0.5 square plus 0 square will give us 0. So this gives us 3.536. So this magnitude is 3.536 approximately, and this is in meters, right? So this magnitude is in meters. Now we can say that the unit vector from A to B is equal to 3.5 divided by 3.536 I plus 0.5 divided by 3.536, this is j, and this will become 0 divided by 3.536 will give us 0. So this is the unit vector from A to B, and 3.5 divided by 3.536, this gives us 0.989 I, and then 0.5 divided by 0.536, this is 0.5 divided by 3.536, this gives us 0.141. This is plus 0.141 j plus 0k. This is 0k and this is 0k. So this is the unit vector along that AB line about which we want to find the moment. And now we have to find, in this equation, we have to find the position vector from B to D. Now to find the position vector from B to D, we need to travel from B along the x, y, and z axis to reach that point D. So now the position vector from B to D is, we can say that from B, we need to travel 0.5 meters in the negative y, and then 1 meters in the negative x. So 1 meters in the negative I, and 0.5 meters, this 0.5 meters in the negative j. So I will write minus 0.5 j. This is minus 0.5 j, and then we will reach here, and then from here we need to travel this 4 meters, this 4 meters in the positive z. So we will reach that point D from B. So this is plus 4k. Now this is the moment arm for that force F to find the axis, the moment about the axis AB. Now we are given that force F as a Cartesian vector. We can write that force F as a Cartesian vector. This is equal to, that is given as a 50I minus 20j minus 80k. So now using that equation, this is our equation. Let me copy it. We can use this equation now to evaluate this, to find this magnitude of MAB. We need to write it in a determinant. Let me write the determinant here, since we will require a lot of place, right? So this is, first of all, we have to write the first row of this matrix will be the unit vector, the component of the unit vectors. So we need to write UAB, the components are 0.989, 0.141. So we have to write that as a first row. This is 0.989, 0.141 and 0. And then the second row will be the position vector from B to D, the components of the position vector from B to D. So now from B to D, this is our position vector, so we will write minus 1, minus 0.5, and this is 4. And the third row will be the components of that force F. So that is 50, minus 20, and minus 80. And now we are going to use that unconventional method to determine the determinant of this matrix. So I will write first two columns again. So this is 0.989, 0.141, minus 1, minus 0.5, and this is 50, and this is minus 20. So this MAB, the moment of that force F about point AB, this will be, we need to take the product of this and this. So this is 0.989 into minus 0.5 into minus 80. This is minus 80. Then we need to multiply this. So this is plus 0.141 into 4 into 50. And then we need to multiply this. So this will give us 0. This is 0. And then from from the other side we have to multiply this 50 and this, so and with the negative sign we have to subtract these ones, right? So this is 0, so we will write that this is 0, and then we have to take the product of this and we have to write that minus sign, right? So this is minus 20 into 4 into 0.989, and then we have to take the product of this with minus sign, we have to subtract this, so this is minus into minus 80 will become plus 80, and minus 1 into 0.141. So when we calculate this will give us the magnitude, the determinant of this given matrix. So this is 0.989 into 0.989 into minus 0.5 into minus 80. So this is, so the first term gives us 39.56. Then this second term is 0.141 multiplied by 4 multiplied by 50. This is 28.2. Then we have 0 plus 0, and then we have this minus into minus, so this minus into minus is plus, so 20 into 4 into 20 into 4 into 0.989, this gives us 79.12. So plus, this is plus 79.12, and then this last term is 80 into minus 1 is minus 80, so minus 80 into 0.141, this gives us minus 11.28 minus. Now we have to add up all these. So the first term is 39.56 plus 28.2 plus 79.12 and minus 11.28. So this gives us 135.6. This is 135.6 Newton meter, or we can say that this is approximately 136 Newton meter. So the moment of that force F about the AB line is equal to 136 Newton meter. Now in the second problem we have to find the moment about BC line. So to find the moment about BC line, let me make a copy of this. Now again, to find the moment about BC, let me write that equation. The moment about BC will be equal to the unit vector along BC dot product with the position vector cross F. Now the position, we can use that same position vector since we want to find the moment about BC. So this is our BC line, and the position vector or the moment arm can be any vector from this BC line to the line of action of that force F. So we can say that this CD can be the moment arm, or we can say that this BD can be the moment arm. So since we have determined that position vector from BD, so we will use that same moment arm, right? So the position vector from B to D can be considered as the moment arm for finding the moment about this BC line. You people can find this moment about BC by using the position vector from C to D as a moment arm. So you people can check your answer by finding the same moment by using the position vector from C to D. So we people will get that same answer. Now I am going to find this moment about BC by using the position vector from B to D as a moment arm. So now we have to find again the Cartesian vector representation of all these. This is the unit vector, the position vector from B to D, and that force F. So the unit vector from B to C will be equal to the position vector from B to C divided by its magnitude. Now for the position vector of B to C, again we need to travel along the x, y and z from B to reach that point C. So from B we need to travel this distance, this is 2 plus 0.5, so this is 2.5 in the negative I. This is the positive y direction, so we need to travel in the negative y direction, so that is minus 2.5 in the negative j direction. This is negative j, and then once we reach here we need to travel this distance in the negative x, so this is minus 1.5 in the negative I, and there is no need to travel in the z direction, so that will become 0k, and then we have to determine its magnitude. So its magnitude will be the square of each component by using the Pythagoras theorem. So this is 1.5 square plus 2.5 square plus 0 square. So this will give us 1.5 square plus 2.5 square plus 0. So this gives us 2.662. So this is approximately, this is 2.5, right? So this is 2.915. So this is approximately 2.915 meters. The magnitude of this position vector from B to C is 2.915 meters. Now we can write that the unit vector from B to C is minus 1.5 divided by 2.915. This is in the I, then minus 2.5 divided by 2.915 in the j, and then 0 divided by 2.915 will give us 0. Now 1.5 divided by 2.915, this gives me 0.515 I, and then 2.5 divided by 2.915, this gives us minus 0.857j plus 0k. So this is the unit vector from B to C. Now the position vector from B to D, we have already determined that position vector from B to D. So let me copy these two, since we are going to use these two again. So now we have these three vectors which we are required to evaluate this, So now we can write that as a determinant. So this is the moment about BC line, the magnitude. This is equal to, so the first row will be the components of the unit vector from B to C, which is 0.515 minus 0.857, and this is 0. This is also negative. Remember that this is also negative. This is negative, right? So we have to write minus sign here. This is minus. So minus 0.515 minus 0.857 and 0. And then the second row is the position vector from B to D. So we have to write minus 1 minus 0.5 and 4. And then the third row is that component of that force F. So this is 50 minus 20 and minus 80. And again we have to repeat that unconventional method to determine this determinant. So this is minus 0.515 and minus 0.857, minus 1 minus 0.550 and minus 20. Now we need to multiply these and then these and then these. So we have to write that this is MBC. So this is minus 0.515 into minus 0.5 into minus 80. Then we have to write this. So this is minus 0.857 into 4 into 50, and then this will give us 0 into minus 1, right? Now then we have to take the product of this. This will give us 0, then and then we have to subtract this. So this is minus, we have to write minus into minus 20 into 4 into minus 0.515, and then we have to multiply all these with minus sign since we have to subtract it. This is minus into minus 80 into minus 1 into minus 0.857. So now we have to evaluate all these terms. So the first term is minus 0.515 into 0.5 into minus 0.5 into minus 80. So this gives me minus 20.6, and then minus 0.857 into 4 into 50. This is minus 171.4. And then the third term is minus into minus. This minus into minus is plus. So this is 20 into 4 into minus 0.515. This is minus 41 point. And then this is minus into minus plus. This is plus 80 into minus 1 into minus 0.857. This gives me 68.56. This is 68. Now we are going to add all these. So this is minus 20.6 minus 171.4 minus 41.2 and then plus 68.56. So this gives us minus 164.64. So now this minus sign tells us that this is in Newton meter, and the minus sign tells us that the given force is producing the moment about BC line in the opposite direction, right? So since we have considered the position vector from B to C, we have considered the position vector from the unit vector from B to C. This is our unit vector from B to C. So the answer gives us that the moment about BC is minus 164.64 Newton meter. So now the negative sign tells us that the moment is in the opposite direction of the unit vector. So the unit vector is from B to C. The unit vector is from B to C, and the moment produced is in the opposite direction of B to C. So the moment is in the opposite direction of that unit vector. And now if we direct our thumb in the direction of this C to B, in the direction of the moment in this direction, if we point out our thumb in this direction and if we curl our right hand finger, so that will give us the direction of the moment about that BC line. So the moment produced by the force F about BC line is like this. Now if we curl our right hand fingers in this direction, so the thumb will point out in the opposite direction of that BC line. So the negative sign tells us that the moment produced by that force F about that BC line is in the opposite direction of the unit vector that we have used. So we have used the unit vector from B to C, and we got the minus sign with the moment. So the minus sign tells us that the moment direction is in the opposite direction of that unit vector from B to C. So this tells us that the moment from B to C is the moment about B to C is from C to B, and that moment has a magnitude of 164.64 Newton meter. So this is the solution of this particular problem. I hope this will help you in your learning. Do subscribe my channel.